Welcome students, welcome to the next session of Strength of Metals 1. So in the previous classes we have given shear stress distribution for the sections. We have already done for rectangular section, circular section, and there we mentioned for the I sections we will go into a numerical, right? So for the I section we are going to generate a shear stress distribution diagram across the depth of the beam. Okay, as you already know, when you see any cross section, rectangular shape is there, that I call it as rectangular section. Circular cross section, when you observe, circular section we say. Here our beam, when we see the cross section of the beam, you can observe the I section shape. Okay, so I am going into a numerical for the I section. Okay, firstly read the problem what they have given. An I section 150 mm by 350 mm has a web thickness of 10 mm and flange thickness of 20 mm. First, you should have to think or remember what the things they are asking. So, firstly, they have mentioned there is an I section shape. Okay. So, in that I section, they are having some dimensions and those are two dimensions only. Like a rectangle, they have given two dimensions like B by D. Yes. So, this one is width of the beam and this one is they indicated as the whole depth of the beam. If you want, you can write it as capital B also. So, the rectangular section's dimension B by D they have given. And they have given two terms. One is web, another one is flange. Right? So, these top and bottom levers, we call it as flanges. This one is also flange. So, top flange and bottom flange. And the portion which is vertical, we call it as web. Okay. So, we are having flanges and web. Okay. Now, the dimensions of those flanges and web. See here, 10 mm is the thickness for the web. So, as the web is like this and thickness of the web means the dimension which it is involving. This one is 10 mm. And also, we are having the dimension for the flange thickness. So, the flange thickness is 20 mm, right? So, the thickness of the flange they are using is 20 mm. Okay, this is also 20 and this is also 20. So, in this way, they have given the section and they have mentioned the width of the beam which is B by D. B measurement is 150 mm and depth of the beam D measurement is 350 mm. Right? So, in this way, our calculation cross-sectional with the dimensions the detailing was over. Now, what we should have to do for this I section? As this I section or if the shear force acting at the section is 40 kilonewtons, right? So, they have given the shearing force acting at the section and we should have to find the maximum shear stress developed in the I section. Generally, when you see this shear stress we should have to calculate. Okay, shear stress I need to calculate from the formula which is F A Y bar divided by I into B, where that capital F is indicating the shearing force acting at the section only and this tau is indicating at a level where we are calculating the shear stress. At that position it will give the answer. Now I am thinking about where that shear stress will be maximum. So I should have to calculate the along the depth or across this depth. What is the shear stress? One point will have one shear stress. Like we have discussed in bending also. Here also one level will have one type of shearing stresses. So in those shear stresses, what is the maximum shear stress that I need to calculate? So before entering into what is the maximum shear stress, what I can say? I can say the maximum shear stress will occur at the neutral axis. Bending stress is 0 at the neutral axis. Maximum shear stress will occur at the neutral axis. Okay. So that thing you should have to remember. Okay. Now at the neutral axis the shear stress will be maximum. Okay. At the neutral axis tau max is equal to shear stress at the neutral axis level. Now where is the location of the neutral axis? As I already know, this I section is being symmetrical with respect to horizontal and with respect to vertical. So this was a purely symmetrical I section. So, for the symmetrical I sections, rectangles, circles, squares, what is the location? for the neutral axis. So, the geometrical center line, when we see the whole depth, half the depth, there is a line that we call it as geometrical center line. Now, at the geometrical center line level, there will be axis. That axis is the neutral axis. Okay. Generally, neutral axis is centroidal axis. And here, being it as a symmetrical section, geometrical center line is also passing through that. Okay. Geometrical center line means total depth by 2. From the bottom, total depth by 2. From the top also, total depth by 2. That is the geometrical center line. So, that is the location for neutral axis. Why this is both are coinciding? Because the I section is symmetrical. See, when you see the section, they have given as 40 kilonewton shearing force, and they have mentioned the I section is having some dimensions for the flange and web, and also the overall dimensions they have given. And involving all these things, we have finalized one more term, that is the neutral axis line will pass through the geometrical centroidal axis. Okay, so as this one is 350 by 2 and this one is 350 by 2. So this is the measurement, and I know this one is 20 and this one is 20. Only for the purpose, I am calculating the remaining portion which is left here. That value is 310 mm. Okay, just for the future sake, I am writing this value, and this is 10 mm we are writing as it is. Generating the section is important. You should have to draw the figure. When after seeing the problem, we should have to generate the cross section, and we should have to indicate the neutral axis, and then we should have to go into the maximum shear stress calculation, because at the neutral axis level only maximum shear stress will come. Okay. Now, the given data, what they have given, that capital F is equal to 40 kilonewtons, which is 40 into 10 cube newtons. Now, and capital I is moment of inertia of the whole section about the neutral axis. Moment of inertia of the whole I section about the neutral axis. As our I section is like this, when you want to calculate the moment of inertia, even in your previous semesters also you have completed calculating moment of inertias for different sections, even for the curved portions, right? But here I am having simply rectangulars, but a number of rectangles were connected and formed as a I section. Okay, when you see this, you can observe these levels. Okay, so either I can calculate the moment of inertia considering one segment, another segment, and third segment. So summing up 3 segments moment of inertia I can calculate, or any other way for calculating the moment of inertia for the symmetrical I sections. Remember, for the symmetrical I sections, the way we can choose is simply for the rectangle. See here in the problem how they have given, like that I am taking the I section, a rectangle of 150 by 350. If the rectangle is solid, 150 by 350, okay, be d cube by 12, 150 into 350 by 12. But in case of I section, is it solid? No. Some portion was removed from the sides. How much portion they have removed? So, the removed portion is like this. Okay. Now, we have already given for the section modulus. There also we have seen rectangular, hollow circular, right? So, here also, for the I section, some portions of moment of inertia I am taking out. If it is a solid, this is the moment of inertia. But some portion it is not there. Okay. This portion and this portion is not there, right? So these portions moment of inertia I should have to take out. As this is 10 mm and out of 150, taking out this 10 mm, what is the remaining portion? That remaining portion is 140. to the removing portion width. How much I am removing? 140 dimensions portion I am removing with width. And what is the depth of the removing portion? The depth of the removing portion is this height. And this height we have already calculated and got the gap measurement. This measurement as 310. Right? The previous step only we have generated. So, the removing portion's depth is 310. So, out of 150, 10 is still there. Even though it is half this side, but out of 150, 10 is there. Wherever is the location, but that vertical 10 is there as it is. So, the remaining 140 width we have taken out. So, that 140 is the taking out moment of inertia's width and 310 is the depth of the material I am taking out. Okay. So, 140 into 310 cube divided by 12. So, the first portion is coming from the solid section. So, only from the rectangle with 150 by 350 BD cube by 12. But it is not a solid value. It is taking out something. So, that taking out portion I have calculated that width as 150, depth as 310. So, these portions of moment of inertia I should have to subtract. So, original BD cube by 12 minus how much I am taking out, the BD cube by 12. Now, the overall moment of inertia of the I section involving those two terms. Okay, I have got this answer as this moment of inertia. Okay, and I have already said not only this way, I can solve in another way for the moment of inertia also. That I am going now. Okay, this is involving 3 segments moment of inertia summation. Right? Okay, the overall I section has split into 3 parts. The first one, the second one and the third one. So, the moment of inertia capital I of the whole section is equal to I1 plus I2 plus I3. Summing up all these 3 moment of inertias individually will give the output of the answer. Okay. And how I can calculate this I1? See here, when I am observing only that segment, I should have to observe that segment only, not the remaining ones. Okay. So, I am drawing the neutral axis line and I am giving the top flange only. Only about the neutral axis I should have to calculate. That neutral axis I have given and the top flange of 150 by 20 I have drawn. Okay, so only for this top flange I should have to calculate the moment of inertia. Now, about the neutral axis for the first slant or for the first flange, B 150 into D BD cube by 12. If the centroid is passing through this, no problem. But this axis is distant from the centroid of the original. Sorry. This A into y square will come. Okay. So, what is this A? A is area of the segment what you are seeing now. 150 into 20. BD cube by 12 plus 150 into 20. And what is y square? Y is distance of the centroid of the top flange from the neutral axis. Distance of centroid of the top flange from the neutral axis. As its centroid will be 10 from top and 10 from bottom. Right? It is a rectangle, so centroid will be at half the depth. So, now the total I have got the value as 350 by 2. What is this 350 by 2? From this outer to the neutral axis, that is 350 by 2. See here, up to this portion is 350 by 2. Now, in the 350 by 2, how much I should have to remove? How much portion I should have to remove? That is minus 10. Because this total is 350 by 2. And I should have to write distance of a centroid from the neutral axis. So, from the neutral axis to the centroid, what is the distance? That measurement only I should have to write here. Okay. BD cube by 12 plus A y square. See here, as it is I have written B D cube by 12 plus A into what is y. So, half of the distance of 350 is overall. In that 10 is removing. So, the remaining 350 by 2 minus 10 is the perpendicular distance of the centroidal axis of the top flange from the neutral axis. If it is the location, then this is our Y for the top flange. Okay, now for the second, what is the second one? That one is web. Okay. And for the second portion, what I should have to do? Only the web portion and indicating the neutral axis. As we already said, overall 350, at the center the neutral axis will pass. Now this web portion is having a height of 310 and the web thickness of 10 mm, right? Now for this web portion also, the neutral axis is passing at the half the depth only, which is 310 by 2, which is its original centroidal axis of the web. Okay, so the web is having the centroid somewhere, and through the same centroid only this neutral axis is passing. So when I am calculating moment of inertia about its own centroidal axis, I will get the moment of inertia as BD by 12 only, not AY square. When the AY square will come, if the centroid of the portion, what I am calculating the moment of inertia, and the axis, when these two are distant, at the time AY square will come. If the centroid of the portion and the axis which we are calculating the moment of inertia, both are coinciding, as you already know, the moment of inertia for this second portion or the web, the centroid will pass through this, and the original neutral axis is also same. So about the axis which is passing through its centroid, I am calculating the moment of inertia. That's why moment of inertia for the second member, that is web, BD by 12 only, as it is the value only will come. What is B and what is D? Which measurement is parallel to the axis? Okay, NA is having some axis line and the measurement 10 is parallel to NA. That's why B, and depth is 310. Okay, 10, 310 cube divided by 12. So 10 into 310 cube divided by 12. And the last segment is the bottom flange. Now for the bottom flange, what we should have to do? Again, as it is like first one, this one is the second one, and now I am going for the third one's answer. Okay, I am going for the third one. Ready? Only axis line. What is the bottom flange? That only we should have to draw. B T cube by 12. When it is passing through its own centroidal axis. So when I am calculating the moment of inertia about its own centroidal axis, B D cube by 12, 150 into 20 cube divided by 12 plus how much I can do? Again, being a parallel axis theorem, A into Y square. So the Y measurement will come from this Y, and multiplication of these two will give A. So 150 into 20 cube divided by 12. So 150 into 20 cube divided by 12 plus 150 into 20. Okay, 150 into 20 into Y. What is Y? Same like the top flange. As we already know, to the bottom, this measurement is 350 by 2. Again, this rectangular section is having the centroid at 10 mm. Now, from this level to the neutral axis level, what is the measurement? Again 350 by 2 minus 10. So, this measurement I am removing. So, this leftover measurement is my Y. So, that remaining measurement is equal to 350 by 2 minus 10, that is Y. So, 350 by 2 minus 10 whole square, A Y square, because Ixx plus AY square, that is the moment of inertia about any axis. So, this is for the third segment. As we have already said, moment of inertia is summation of all the moment of inertias. So, I1 plus I2 plus I3, moment of inertia of all three. Either you can solve in this way, or you can take from the first, a solid rectangular and the removing moment of inertia. In this way also we can go. Okay. So, this is calculation of moment of inertia about the neutral axis. The next thing is calculation of shear stress. Okay. So, for that I have given the formula only for giving the terms so that we can substitute calculations directly. the shear stress at a distance y from the neutral axis is given by. So the shear stress at a distance y, maybe if it is a rectangle and it is the neutral axis, and I am calculating the shear stress at a distance y. Okay, how I can calculate the shear stress at a distance y? That is shearing force acting at the section into this portion will have some centroid at some other level, that is y bar. So area moment of the shaded portion, y bar is centroid of the shaded portion, and that centroid is at a distance of y bar from the neutral axis, and the shaded portion's area I call it as A. Okay, A y bar divided by I times B, I into B, F A y bar by I into B. I is moment of inertia of the section about the neutral axis, B is width of the beam. At the level I am calculating the shear stress. Width of the beam at the level I am calculating the shear stress. Okay, shearing force acting at the section. Those terms I have clearly given again. Okay, the maximum shear stress, and this is the formula for shear stress, and they are asking us to calculate the maximum shear stress, right? So where will be the maximum shear stress will locate? That maximum shear stress will locate at the neutral axis. Okay, so the maximum shear stress will occur at the neutral axis, and that AY bar is equal to first area moment of the portion above the neutral axis, because when I am calculating shear stress at a distance y, from the neutral axis, this is the area. Now what is happening? Calculating shear stress at the neutral axis. So at the neutral axis, to that distance is nothing. So the portion I should have to indicate is A, and this area is having centroid at some level. From that centroid to the neutral axis, there is a distance that is y bar. Okay, area moment of the portion above the neutral axis, because at the neutral axis I am calculating. So above that area I should have to shade, and I is moment of inertia of the section. Only for the reference I am giving the rectangular section. Now we will go for the I section only. Okay, so if it is a rectangle, how we will do? If it is at a distance y from the neutral axis, we will give the level. If it is at the neutral axis, we will indicate the neutral axis level. Above portion we will shade, and for that portion we should have to write the first area moment. And capital I is moment of inertia of the section about the neutral axis, and B is width of the beam at the level of neutral axis. Okay, so because I am calculating at the neutral axis, so every time I should have to use the reference. Area moment for the neutral axis above portion, width of the beam at the neutral axis, because I am calculating shear stress at the neutral axis, because they are asking us to calculate the maximum shear stress, and the maximum shear stress is occurring at the neutral axis, so I am calculating shear stress at the neutral axis. So when you see the whole section, you can observe like this, and we have said above the neutral axis we should have to give the observation completely, not a separate flange, separate web. Only for moment of inertia, for solving that we have taken like a separate portions. Again I have added. Okay, and now at the neutral axis level, when we are calculating the shear stress, that is tau times NA. Okay, this is tau NA. How you will calculate? Just now only we have given the formula FA y bar by I into B. So that F A y bar by I into B. How each individual term comes. Individually we will solve and substitute. Firstly, F in the problem they have given us 40 kilojoules. So F okay. And just now only we have said we should have to consider the portion above the level of neutral axis. Okay, that portion only I have drawn here, and I will indicate it as my portion. Okay, so this is the level I am calculating the shear stress, and above the portion we should have to indicate the observation for the area moment. Okay, A into y bar. Okay, where is that A into y bar will come? A into y bar will come. How it will come? It will come like This one is the first segment. Up to the neutral axis, this one is the second segment. So A1y1 plus A2y2. As you already know, centroid formula, y bar is equal to A1y1 plus A2y2 divided by A1 plus A2. So that I am shifting here. Okay. A into y bar is equal to A1y1 plus A2y2. So what is this A1y1 and A2y2? So first version, what is the area? 150 into 20. And for that, what is the y measurement? Y measurement, how it comes? Y measurement means distance of centroid of the first segment from the neutral axis. Okay, that measurement we should have to write, and it as again 350 by 2 minus 10, only y measurement. Okay, so out of 350 by 2, the measurement I should have to indicate is, this one is 350 by 2 and this one is 310 by 2, right? Because up to this measurement, if it is up to this measurement, that is 350 by 2 and this one is 310 by 2, and this will indicate as y1, and for this also there is a centroid and that one is y2. Okay, now a2 y2. How the a2 y2? Again the second portion. What is the second portion's height? Height of width of the second portion is 10 mm. Height of the second portion is 310 by 2. And where is the centroid comes? Simply it is a rectangle. So for this rectangle, where is the centroid locates? Half of the depth again. So half of 310 by 2, because 310 by 2 itself is the depth, half depth of the web. Again in that half depth of the web, further portion there is a centroid, and that centroid is at half of the depth of the web. So half of the depth of the web I am observing. Okay. In this way, when you calculate, you will get this answer as A into y bar for the neutral axis level. And what is the next step I should have to calculate? In the previous step itself, we have calculated the moment of inertia of the whole section about the neutral axis. Now, we are going for the substitution. And the thing you should have to understand is measurement of B. Okay. So, what is the value of B? B, what we have said, width of the beam where we calculate shear stress. Okay, so what is the width of the beam at the level I am calculating the shear stress, that is indicated as B. Now where I am calculating the shear stress? We are calculating shear stress at neutral axis. Okay, so calculating the shear stress at neutral axis, and at this neutral axis level, width means this one, depth means this measurement. So at the neutral axis level, what is the width of the beam? That is B answer. As the neutral axis is passing through the web, so thickness of the web is width of the beam at the level of neutral axis. Okay, so that width we have got as thickness of the web as 10 mm. Just we already know this measurement. Now, substituting all these answers, tau is equal to tau max at the shear stress at the neutral axis is equal to F A y bar by I into V. F is 40 kilonewton, 4 into 10 power of 3 kilonewtons into A into y bar. In the previous step only we have calculated for the top segment and bottom segment, multiplying these two, we have got this answer 615125. So substituting 615125 here, and then capital I, moment of inertia of the whole section about the neutral axis. So that moment of inertia, we have got this answer. We are substituting the term. Either we can solve like 1, 2, 3 segments, or we can solve like the whole minus removing portion. Anything we will get the same answer. Maybe some decimals we may have changed because so many terms we are involving and substituting and multiplying, right? So with these additions and subtractions, some decimals or some values may differ. That is not at all so much problem. Only the main thing is at least nearby we are getting or not. So that is a cross check also. Any one method you can calculate. Moment of inertia, any method you can choose. Either solid minus some portion removal, or flange moment of inertia, web moment of inertia, bottom flange moment of inertia. Summing up these three also we can calculate. Any one way you can choose. Okay. Now, calculating moment of inertia and substituting. And then B just now only we have said B is width of the beam, where I am calculating the shear stress. That we have got as neutral axis. That neutral axis is passing through the web, and the web's width at the neutral axis is 10 mm. Okay, substituting all these things, we have got the answer as 13.06 Newton per mm square. Okay, so in this way we have calculated the shear stress at the neutral axis from the basics. Okay, without even remembering any formula, only from the fundamental formula, that is tau F A y bar by I into B. So multiplying these terms only, I have got the tau answer, where that F shearing force at the section, A into y bar area moment, and I moment of inertia, and B width of the beam. Okay, so in this way we have calculated. And next we are going for an I section which is unsymmetrical. Okay, so simply first read the problem. What the thing they are asking, we will calculate now. The shearing force acting on a beam of I section with unequal flanges. Okay, flange means the top and bottom, those wings. Okay, so it is having unequal flanges, and the shear force acting on the section is 50 kilonewtons, and the section is shown in the figure. Because for the symmetrical section they have given overall outward dimensions width, overall dimensions depth, and thicknesses they have given. For unequal section, it is somewhat difficult to explain. The top flange is this much thickness, this much width, bottom flange is this much thickness. All these things are somewhat difficult, so they have directly given the picture of unsymmetrical I section. Okay, and the moment of inertia about the neutral axis also they have given. Capital I, moment of inertia of the section about the neutral axis, they have given as 2.894 into 10 power 4 mm power 4 only. And we should have to calculate the shear stress at the neutral axis, and also we should have to generate the shear stress distribution across the depth of the beam. Okay, so over the depth of the beam, what is the shear stress distribution? So what do you mean by distribution? So point to point, what is the value? So on a graph, on a picture representation, we are giving the output. So distribution, how? At a top fiber, what is the shear stress? At the middle fiber, what is the shear stress? Like that, calculating all those and giving on an axis, we will indicate the shear stress distribution diagram. Okay, so this is the unequal I section they have given. So that I section is having 200 mm width and 50 mm thickness. Okay, the top flange is having 200 mm width and 50 mm thickness, and we are having a web portion. So the web portion is a height of 200 mm, and we are having a bottom flange with a width of 130 mm, and its thickness is 50 mm. Okay, so this is the overall I section they have given, and for this I section we should have to calculate the neutral axis. That neutral axis they have not given. Neutral axis we should have to generate. They have only given neutral axis moment of inertia. So moment of inertia of the section about neutral axis only they have given. Okay, so firstly what we should have to do for the unsymmetrical sections, whether it is a bending stress or it is a shear stress, our first output is locating the neutral axis. Okay, so firstly we should have to locate the neutral axis, and then about the neutral axis, if they have not given the moment of inertia, we should have to calculate the moment of inertia also. Later we will go into F A y bar by I into B substitution for this problem. Okay, so individually we should have to observe the picture, and we should have to locate the neutral axis. And generally, what is the location for neutral axis? As the neutral axis is passing through the centroid of the section. So the neutral axis will pass through the centroid. So the neutral axis line is centroidal axis of the section only. So in the next class we will calculate the location for the neutral axis, and we will calculate all the remaining shear stress distribution.